Hello everybody. Just want to make a video on 12.3 where we're learning about the second multiplication for vectors. It's called the dot product. So this is our second multiplication that we're learning. Before we learned the scalar multiplication where you can take a number and distribute it to all of the components of a vector. But now we're talking about, like, if we have two vectors, how do we multiply them? And it turns out that there are two different ways. This is the first one, and it's called the dot product. And it turns out there's a couple of different ways to look at it. Geometrically, if we had two vectors and the vectors were not parallel and they had an angle formed between them called theta, then we could say that the dot product of the two vectors, A dot B, would be equal to the product of their magnitudes times cosine of the angle. Now this notation that's used right here in this little blurb is a little bit off because it's showing the dot product down low, and it should be like something that's directly between two vectors. Okay, so here's what we should be seeing. So that means that if we were given the magnitude of two vectors and we knew the angle between the two vectors, we could calculate the dot product of the two vectors. Algebraically, we don't need that much information in order to calculate a dot product. If we know the components of the vectors A and B, then when we're finding the dot product right here, what we're going to do is we're going to take the first component of A and multiply it with the first component of B. That's right, what we have here. So that's our first product. And then we're going to take the second component of A and multiply it with the second component of B, and that's our second product. And then we'll take the third component of A, multiply it with the third component of B. That'll be our third product, and then we add them all together. So basically, in short, we say we find the product of like components added together. And notice that there are no angle brackets left on this. What we get is a scalar or a number. So the dot product multiplication gives us a scalar. Take two vectors, dot product them, you get a scalar. I'm stressing this because it's important. We do need to be able to express our answer correctly at the end. Few properties of the dot product. Number one, if you take a vector A and you dot it with itself, that works out to being the square of the magnitude, because let's just think about what the square of the magnitude is. Remember, the magnitude is the square root of the components squared, so A1 squared plus A2 squared plus A3 squared. And we're saying that it's the square of the magnitude. Now, if I was to square that square root, they go away, which just leaves us with the sum of the squares of each of the components. The next one is A dot B is equal to B dot A. That is the commutative property. Then we have A dot, a sum of two vectors, is equal to A dot B plus A dot C. That's our distributive property. And then in 4, we have a constant times a vector dotted with the vector. We could just pull that constant out in front of everything and do the dot product first and then multiply by C. Or we could bring C over to B and do A dot CB. And however we do it doesn't really matter. This is an associative property. And then A dot 0 is going to equal the zero number, not the zero vector, but the zero number. That's just showing what the power of the zero vector has there. Okay. Now, the whole idea of the dot product giving us an equation that involves the cosine of an angle means that if we have two vectors and we know what their components are, then we should be able to find the angle that is between the two vectors. So I could just draw a couple of vectors here To symbolize that, here's A and B, and here's theta in between them. So because A dot B is equal to the product of the magnitudes and cosine of theta, that means we can isolate cosine of theta to be the dot product of the two vectors divided by the product of the magnitudes. And then finally, we could take our cosine of both sides, and we get this new sort of formula. Now, you do have one version of this one formula on your formula sheet, so it's not something you have to memorize, but it is something where you need to be able to like go between the two different versions depending on what you need. Now, remember that cosine inverse of 0 is going to equal pi halves, okay? So that means this right here, this implies if A dot B is equal to 0, then the vectors are perpendicular. And so I've got that stated before there. I say two non-zero vectors are perpendicular if and only if the dot product is 0. And then I say it another way. I say if the dot product is 0, then the vectors are perpendicular. I just want to draw attention to these words if and only if. Whenever you see that in math, it means you can read the statement in either direction. So you could say two non-zero vectors are perpendicular if the dot product is 0, or you can say the dot product is 0 if the two non-zero vectors are perpendicular. Okay, so that gives us information, and it gives us a way to test. Like you might be asked to determine, are these two vectors perpendicular? And you're like, I don't know. I'm just looking at two vectors. I have no idea if they're perpendicular. Well, we do. We can find the dot product, and if it's 0, they're perpendicular. If it's not 0, so if A dot B does not equal 0, then the vectors are not perpendicular. Pretty simple. They either are or they're not. Okay, so let's get to an example right away. Let's say that A is equal to a vector with components 2, -3, and 7, and B is equal to a vector with components -1, 4, and 5, and we're asked to calculate the angle between A and B. Now we know from above that the angle between any two vectors is equal to cosine inverse of A dot B divided by the magnitude of A times the magnitude of B. So I can find those three pieces, plop them in, and then go ahead and evaluate. So first I'm going to find A dot B. That's going to equal 2, -3, 7, dotted with -1, 4, and 5. Now to calculate that, remember what we said before, we're going to take the like components and multiply them, and then we'll add those products together. So what that means is I'll get 2 times -1, those are the first components, plus the product of the second components is -3 times 4, plus the product of the third components is 7 times 5. This gives me a -2 minus 12 plus 35, so it's 35 minus 14, which is equal to 21. Then I need to find the magnitude of A, which is going to be the square root of the sum of squares. So it'll be the square root of 4 plus 9 plus 49, which is going to give me, let's see, that is going to be 53, 62, square root of 62. Last piece is the magnitude of B, which will be, again, the square root of the sum of squares. So we have a square root of 1 plus 16 plus 25, which is going to give me 30, 41, 42, square root of 42. Okay. Did I get that right? Yeah, I think so. I'm looking at my work. Apparently I can't square in my work that I have, but I got this right now. Just going to need my calculator to calculate things. So now I'm going to plop everything in. Theta is going to be cosine inverse of the dot product, which was 21, divided by the square root of 62 times the square root of 42. So now I'm going to make sure that I'm in degrees, just because this time I want to have degrees. And I want to find the cosine inverse of 21 divided by the square root of 62 times the square root of 42. And that gives me approximately 65.699, or, well, we'll go to 3 decimal places, so 699 degrees. Depends on what WebAssign's asking you for. If they're asking you to round to the 10th place, then this would be 65.7. The 100th place, it would be 65.70, and so on and so forth. Okay, next, let's see what we've got. Direction angles. Okay, so our particular vectors in 3 space, there are 3 axes that any one position vector could make an angle with. So up above, we were just taking 2 vectors and finding an angle between them. But down here in the direction angles, what we're going to be finding is first, like this alpha right here, that is the angle that a vector creates with the positive x-axis. Beta is the angle that a vector makes with the positive y-axis, and gamma is the angle that a vector makes with the positive z-axis. Now remember, each axis can be represented by a standard basis vector, and so remember with the x-axis, so if we just write this out, I'm going to write it in green to match. So for an example, with the x-axis, if we were to go ahead and use what we know from up above, that alpha is going to be the cosine inverse of the dot product of the 2 vectors involved. Well, the 2 vectors involved are v, this vector right here, and then the standard basis vector that represents the x-axis, that's going to be I. So it'll be the dot product of v and I divided by the magnitude of v times the magnitude of I. Okay, but the standard basis vector I hat only has one non-zero component, and that's going to be the x component will be 1, the y component 0, z component is going to be 0 as well. The other thing that the I hat vector has going for it is that its magnitude is 1. And so when this simplifies, let's see, we've got cosine inverse of, just so we see it for giggles, v1, v2, v3, dotted with 1, 0, 0, divided by the magnitude of v times 1, because the magnitude of I is 1. And now see in the numerator, when I do that dot product, it's just going to give me the cosine inverse of v1 over the magnitude of v. And that's it. And so I derive this up here just so you can see how we're coming up with it down here. And then we can do a similar thing to find the angles between the vector and the y-axis, and then between the vector and the z-axis. And each time we use the standard basis vector as the other vector. That way, this whole direction angle thing is no different than finding the angle between 2 vectors. Okay. So let's see, we've got our same 2 vectors again, 2, -3, 7, that's A, and B is -1, 4, 5. We are asked to calculate the direction angle between A and the z-axis. So the z-axis vector can be defined to be the k-hat vector, which has components 0, 0, 1. Okay, so if we want to find the angle between A and the z-axis, we have a name for it. It's called gamma. It looks like this. It is equal to cosine inverse of A, which is our 2, -3, 7, times k, which is 0, 0, 1, all divided by the magnitude of A, which will be 4 plus 9 plus 49, times the magnitude of k hat, which is 0 plus 0 plus 1, just so you see this in all of its calculation glory. This gives me cosine inverse of On top, I'm left with just a 7. In the bottom, I'm left with the square root of 62. And that's it. So now when I plot this into my calculator and calculate it, I end up with an angle of approximately 27.25 degrees. And that is the angle that this vector A will make with the z-axis. All right. An application that we could see for these dot products, something that we can do with them, is they're called projections. And the way I like to think of projections is using this idea of walking under a lamppost at night and then watching your shadow. And if you think of your body and the ground as vectors, then your shadow is the vector projection of your body onto the ground. And if you think about it, as you walk away from a lamppost, your shadow gets super long, and then there comes a point where you're so far away that you don't see your shadow anymore. The length of your shadow is a scalar projection of your body onto the ground. And so the scalar projection tells you just length. And the vector projection tells you a vector. And so that has a direction, right? Also has a magnitude, but it's not obvious what the magnitude is. The scalar projection will tell us the magnitude. So length or magnitude. Okay. And so what your job is to remember is that when you're asked to calculate a vector projection, you're being asked for shadow length, or you're being asked for the shadow vector, And then if you're asked to calculate a scalar projection, you're being asked the length of the shadow. And your book has a few nice little pictures of a projection. In these particular pictures right here, the idea is that there's like a light shining directly above. And so a slanted longer angle that is, lifted off the ground, if a light's shining directly down on it, the projection just goes straight to the ground. And we want to know, what is that projection of B onto the floor A? And that's going to give us a vector. And then, of course, we could go in the other direction if B is pointing, towards the second quadrant or something like that. And we want to know what is the projection of B onto A. We're just going to think of the flashlight shining directly above, and B will flop down and be this red vector down here. And that's our projection vector. Okay. So here are some formulas for that. The scalar projection of B onto A, the notation's a little weird. We see this comp and then a little a that's kind of the down low, and it actually is down low, and then B. And the way we read that is component of B onto A. And then the vector projection of B onto A, we use this notation right here, this proj, and then a little a down low, and then a B. And this is saying projection of B onto A. Okay, so notice in the scalar projection, the component of B onto A, in the numerator we have a vector projection. We have a dot product, and that is a scalar. In the denominator we have a magnitude, and that is a scalar. So overall, we get a scalar. And so when you're calculating a scalar projection, you should expect a number, and that is going to be the length of the shadow. If you're getting a vector, then you did not just calculate the scalar projection. The vector projection, on the other hand, notice in this format, there's a factor in here that is exactly the scalar projection, A dot B over the magnitude of A. That is just a number. Remember, it's a multiplier. And then A over, so let's see, let's label that. That's our length. And then the A over the magnitude of A, that is a unit vector. So the projection of B onto A is a unit vector times the length, where the length is coming from the effect of B onto A. Okay, and then in short, we have this final version for our calculation. But notice that if you're asked to calculate both scalar and vector projections, once you calculate the scalar projection, you can just kind of plop it into the vector projection, find your unit vector, and then multiply them, and you're done. So let's see how that's done. We have the same two vectors, A, 2, -3, and 7, and B, which is -1, 4, 5, and we're asked to calculate the vector and scalar projections of B onto A. So the scalar, that's going to be the component of B onto A. I really stress my A down low so I don't get confused. And from the formula up above, it's A dot B over the magnitude of A, which is going to be the 2, -3, 7, dotted with -1, 4, 5, all divided by the square root of 4 plus 9 plus 49. That's the magnitude of A. On top, our dot product is going to give us -2 minus 12 plus 35. In the bottom, we have the square root of 62. And finally, we get 21 over the square root of 62. And remember, we can think of this as the length of the shadow. Okay. Now the vector projection, that's where we're going to look at this projection of B onto A. And we're told that that's A dot B over the magnitude of A squared times A. And you can calculate it this way, and we can still use what we calculated above because it's almost the same. The A dot B is still going to be 21. The magnitude of A is still the square root of 62, but now we're going to square it. Then we multiply by the vector, 2, -3, 7. And when I say we multiply by the vector, I mean good old-fashioned multiplication by a number, because the 21 over the root 62 squared is just a number. So that's going to stay on the outside. It becomes 21 over 62 times the vector, 2, -3, 7. And that is our vector, our shadow vector. All right. Another application of the dot product is with, well, we're actually kind of still using the same formula, if you will, that we did when we were looking at the angle between two vectors. But we're using the general definition of the dot product of two vectors being equal to the product of two magnitudes times the angle between the two vectors. So if we know the work done by a vector force, F, in moving an object through, if we know, we won't know the work done, but let's say that we know a vector force that's being used in moving an object through a vector distance, then we can calculate the amount of work that takes, like how much work is done. And sometimes we'll be given the angle between the two vectors, and we'll be told the magnitudes of the vectors. And so then we'll use this first form. And sometimes we'll just be told the two vectors, and then we'll use the second form. More often than not, we use the first form. It all just depends on what you've been given in your particular problem. So let's look at this last example here. We have a wagon, and it's pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. The handle of the wagon is held at an angle of 35 degrees above the horizontal. Find the work done by the force. So the first thing we need to figure out is, what we've been given. And we need to remember that work is the force vector times the distance vector, or it's the magnitude of the force times the magnitude of the distance times cosine of the angle between them. Now, it looks like we have been given the magnitude of force. this right here, when we're told that there's a constant force of 70 newtons, we're being told the magnitude. So the magnitude of force is equal to 70 newtons. We are also told theta is equal to 35 degrees. And then we're told that d, our distance vector, so the wagon is pulled a distance of 100 meters along a horizontal path. That means it's not moving vertically. So we have movement that is all x, so the x component is 100, and the y component is 0. Now it's fairly easy to calculate the magnitude of d. It's just going to be the square root of 100 squared, which is just 100. That means that we can calculate our work using the magnitude of F times the magnitude of D times cosine of theta. Putting everything in, I have 70 newtons for the force vector. I have 100 meters for the distance vector. I'm going to go ahead and put my meters there. And then I have cosine of the angle, which is 35 degrees. And then I can pop this into my calculator, and this is going to give me approximately 5,734.1 Newton meters. And those of you who have taken physics may recognize Newton meters as joules. You can leave it either way, however you like. Okay, I think that is it for 12.3. It is. So the next time we meet, it'll be 12.4. If you have any questions on this at all, please reach out.